We're going to work on problem 1 from the practice exam for Material Science Engineering 45 Exam 2. So this question covers Lecture 6 material, so all about curvature, chemical potential, where will grains move, where will grain boundaries move, how will grains grow, how will 2D grains grow, how will particles, three-dimensional particles, and we're talking about dealing with Oswald ripening, how will those particles grow with time, what's the scaling, and then also homogeneous nucleation, heterogeneous nucleation, all those kind of good things. So let's go ahead and jump right in and get started on this problem. So question 1, curvature, growth, shrinking, and scaling. Interviewing for a job at Valmet, metal powder company here in Stockton, they give you the following images, and it's asking you, will grain X or Y grow? How did you determine that? How will the grain growth scale with time? What tunable parameters do we have at our disposal? Point out explicitly in the equation for 2D grain growth. So first, let's answer the first part of this question. Will grain X or Y grow? So this is a 2D grain. So we know if we have a 2D grain, we have this equation for grain growth. So we might as well write it out right now. So R bar squared minus R naught. So the average particle size here minus the initial average particle size squared equals 8 the surface tension of the grain boundary, MT over K. This is a constant, and we'll dive it. Actually, let's go ahead right now. M is equal to kind of that huge kind of parameter, this kind of long equation. I'd have it written down or kind of ready at your disposal for the exam. So A is a constant, tau is a hopping parameter, another constant, and number of particles is going to be constant, basically. V bar molar volume squared over Avogadro's number and A times K, Boltzmann's constant, times T, times exponential of minus delta G activation energy over KT. So let's leave this. Actually, we could kind of leave this alone for a second, but let's answer this first question. So for 2D grain growth, how do we know whether a grain will shrink or grow? Well, we're going to use, for 2D grain growth, the von Neumann n equals 6 principle. So if n equals to 6, our dr dt is equal to 0. If n is greater than 6, we are going to grow. So our dr dt is greater than 0. If n, excuse me, let me clean this up here. I'm going to write it over here. So I'm going to write if n is greater than 6, our dr dt is going to be greater than 0. If n is less than 6, our dr bar dt is going to be less than 0. Sorry for that, this kind of messy handwriting. But again, you all know this rule now by heart. So let's go ahead and see, will grain X shrink or grow? So I've got 1, 2, 3, 4, 5, 6 sides. So X, our dr dt, it's neither going to shrink or grow. What about Y? So I've got 1, 2, 3, 4, 5, 6, 7. So the number of sides, n, is greater than 6. So Y, our dr dt, is greater than 0. So we will grow here. So we've answered that question. How do we determine that? Von Neumann n equals 6 principle. How will the grain growth scale with time? So we actually already have, I got to mess with that expression. We already have this expression right here. So we know that R bar from this expression is going to scale as t to the 1/2 for 2D grain growth. So we've got the scaling, so that's done. What tunable parameters do we have at our disposal to change the grain growth? So we've got to just, as I was writing this question, the expression down, we saw that this is basically a constant for whatever material you pick. This A is a constant. So really the only parameter in here that's going to change is n. So m, so this is a constant, this is a constant, this is a constant. Once you choose your material, constant, definitely constant. These are constants. And again, this will be a constant as well, relatively speaking. So what you're left is with a temperature on the bottom here, and then an exponential temperature growth here. So in your equation, m is the parameter that we can change, and we can change this via temperature. Temperature is our tunable parameter here for this expression. And that's it. That's all you have to do for this first problem. So let's go ahead and look a little bit deeper into this problem. Or let's go to part B. So part B, at the interface denoted by the green arrow, will grain A or B, so is this grain boundary. So will this, let me erase that, now I can't see. So will this grain shrink, or where is it going to move? Will A or B grow? So we need to write the expression for chemical potential at the interface and explain where atoms will move. So we know that generally speaking, so for chemical potential of a sphere, is going to be our chemical potential of an infinite plate plus or minus 2 gamma GB times molar volume over R, where this plus or minus depends on whether curvature is positive or curvature is negative. So for B, oops, let me fix that. So the chemical potential of B is going to be chemical potential of an infinite plate. Now, if I'm sitting right here, is my curvature positive or negative? My curvature is positive, so it's going to be 2 gamma GB molar volume over R. My chemical potential of A is going to be, I'm sitting here, is my chemical potential positive or negative? It is negative. V bar, or 2, excuse me, V bar, gamma, B, I'm going to scroll down just a little bit, over R. So, where are atoms going to flow to? So we move from, again, areas of high chemical potential to areas of low chemical potential. So let me erase this right here. So the atoms are going to flow from high chemical potential here to low chemical, atoms are going to flow from high chemical potential to low chemical potential. So they're going to flow out over here. And this grain is going to grow this way. So that grain boundary is going to move in. Part A is going to grow, B is going to shrink. So that's it. So we've got, will A or B grow? We've got the expression for chemical potential, and we kind of explained already, it's this driving force for moving away, or moving, away from this idea of moving from high chemical potential to low chemical potential based on curvature. And then it says, additionally label the wells in the Bell reaction curve shown below, which corresponds to A and B. So let's go to the next page. So we knew from, let's go back to, atoms want to flow from B, high chemical potential, to A, low chemical potential. So which well are we going to kind of label here? So we want to flow from, again, oops, let's go here. We want to flow from B to A. So the easiest jump that's going to have is B to A, right? Atoms want to go from here to here. That's it. So again, because it's going to be harder, atoms don't want to go from A to B. So we have to jump that entire kind of length here to go from A to B, whereas to jump from B to A, all we have to do is just jump this kind of barrier right here, and you're good to go. Yeah, that's it for that part of B. So we've answered A, we've answered B. It says Valmet is impressed with your nucleation and growth knowledge in 2D, but they decided to take it a step up and ask you about 3D Oswald ripening. Give your growth rate of spherical particles, and giving you a growth rate of spherical particles shown below. So for the image below and the plot below, it's asking what is the average particle size in each experiment, A, B, and C? For what systems will a 45 micrometer particle grow? How will the growth scale in time? And what assumptions did we make here? So that is, again, quite a few questions incorporated in this graph. So let's go below here. So we need to figure out, will a 45 micrometer particle grow? And we are dealing with Oswald ripening, so we know that we have basically this expression here. So dA dt is equal to minus 2 C naught d v bar squared gamma SL divided by RTA. And we have 1 over A minus 1 over A bar right here. So from this expression, what particles are going to grow and what particles are going to shrink initially? So if my A, my particle size, is less than A bar, so there's a negative right here. If my A is less than A bar, so let's say my A is 1 over 10 minus 1 over 100. What's the sign here in this kind of parameter, or in this guy right here? Well, this is positive, right? And then this is negative. So if A is less than A bar, dA dt, erase that. So let's go back to this. So yes, if your particle size is less than your average particle, if your particle size is less than the average particle size, your particles will shrink. If A is greater than A bar, now it's the flip scenario. So if it's 1 over 100 minus 1 over 10, now this value is negative times a negative, our dA dt is now going to grow. So now we have to figure out, okay, we're trying to figure out, will a 45 micrometer particle grow in these three experiments, A, B, and C. So the first thing we have to do is figure out for A, B, and C, what is A bar? So how do we figure that out? Well, we know that we figured out that the fastest growing particle size, so when dA dt, when you take the derivative with respect to A and you set it equal to 0, you'll find that your fastest growing particle size, A, will occur is equal to 2A bar, so A max. So your fastest growing particle size is twice the average particle size here. So if I take the derivative of dA dt with respect to A, what am I finding, and setting equal to 0, what am I finding? I'm finding maximum values, right? So I'm finding the values here, here, and let's say over here. So all I have to do now is go down here, figure out where it crosses my x-axis, like so. Same thing here, and that equals whatever this value is. That is equal to 2A. So let's look at kind of the units here. So we're taking like basically 1, 2, 3, 4, 5. So we're looking at basically tens. So here, this is 50 microns. So even over here at 50 microns, this 50 microns is equal to 2A, right? 50 micrometers. Let's say if we had a maximum that hit right here, this is equal to 2A bar. So my A bar, even if I had a maximum at this point, my A bar would be 25 micrometers. So in which systems will a 45 micrometer particle grow? So we know that all of these are going to be less than, out here we're at 50 micrometers. If we, again, if and our average A bar is going to be 25 micrometers even here. So here we're even less. So our A bar here, or our A, this particle, our A is greater than A bar for A, B, and C, right? So if our A is greater than A bar, we are going to grow. Larger particles grow at the expense of smaller particles. Excellent. So let's see, did we answer all the questions? Yeah, again, you could get the quantitative values. Again, I'm not too interested in that. How will the growth scale with time? So we know that we also have this expression. So this is dA dt, but we also have our expression for A bar. How does the average particle size in Oswald ripening scale as a function of time? Equals C naught d B bar squared times gamma SL T over 4 RT. So our average particle size will scale as T to the 1/3. Now, also be aware, so this is a constant, this is a constant, this is a constant, this is a constant. We again have two parameters here that we can change, and they both change with temperature. So those are our knobs in this problem. It's not kind of asked for in this equation, but that's what we're going to be working with. And again, the assumption that we make, we cannot solve this problem by separation of variables. We have to solve this equation numerically. So we assume that the average growth, our particle size, the growth dynamics of our system are going to be dominated by the fastest growing particle, this one. So we plug that back in, and then we kind of do separation of variables. That was the assumption that we made to get to this expression. And that's all in the notes. So last part of this question, which curve corresponds to homogeneous nucleation? Which corresponds to heterogeneous nucleation? Also, where is nucleation dominating and where is growth dominating on the graph? Explain how you arrived at this conclusion via the critical amount of undercooling. Which is easier, homogeneous or heterogeneous nucleation? Why, energetically speaking? So we can answer that right now. So which is easier, homogeneous or heterogeneous nucleation in terms of energetically? Why? Well, we know that in homogeneous nucleation, we have a scenario where we're nucleating a solid particle kind of in a vacuum. So we're creating some surface area, assuming we're working with solid spheres, of 4 pi r squared. That's the total surface area we have to create. But in heterogeneous nucleation, we have some type of surface where we nucleate our solid particle. So here, I'm going to call this surface area Homo. Our surface area for hetero is much less than surface area for Homo. Surface area, again, looking at your delta G term, is going to be basically minus delta GV. So this volumetric terms times the volume of your sphere plus your surface energy term times your surface area. We don't want to nucleate particles because we have to create surface area. But there's this volumetric term that allows us or wants to push towards nucleating solid particles. So that is why, if this is the only thing preventing us from creating solid particles. So if we create less surface area, creating surface area is bad energetically. It increases our delta G. If we're creating less surface area, it's going to be easier for homogeneous nucleation or heterogeneous nucleation, excuse me, as compared to homogeneous nucleation. So looking on this curve now, using the same kind of parameter or idea, we need to figure out which curve is homogeneous nucleation. Looking at this steady state nucleation rate. So remember, steady state nucleation rate is composed of 2 terms inside of it. One is our kind of delta G, so from kind of nucleation. So this component, and this component dominates where? At low temperatures. So we want to nucleate at low temperatures. At high temperatures, we have very, very low driving force for nucleation. Again, that is given in that delta GV term. So delta GV, remember, is equal to V is equal to H delta HF times delta T, the amount of undercooling, where delta T, remember, is Tm minus T over Tm. So the more undercooling we have, again, the larger that driving force for kind of nucleation, exactly, for nucleation. So nucleation will dominate at low T, and we have diffusion, because we need to diffuse and kind of our particles in order to nucleate. Our diffusion will dominate at high T. So high T corresponds to low delta T, and low T corresponds to high delta T. High delta T. Excellent. So let's look at this curve. So we know that for heterogeneous nucleation, it's going to be easier because of this kind of argument for. Actually, let's go ahead and before we get into heterogeneous versus homogeneous nucleation, we'll answer that one last. But we just talked about where is nucleation dominating and where is growth dominating. So we've just kind of pointed that out here. So this is a plot of temperature. So we know over here near the melting temperature, our diffusion D is dominating. So on this kind of side you can say on each side of this, on the right side diffusion dominates. On this side, our delta G nucleation. There's homogeneous. That's dominating here. So at low temperatures, nucleation dominates because, again, diffusion is Arrhenius with temperature. Exponential, yeah. Write this out. Equals D naught exponential minus QA T. So as temperature increases, the diffusion increases. As temperature decreases, it's going to decrease dramatically. Here. That's where diffusion dominates. That's where nucleation dominates. Let's look at which curve is heterogeneous and which curve is homogeneous. So heterogeneous nucleation, we're going to be able to nucleate at lower delta T's. So heterogeneous, we're going to start nucleation earlier. So we're going to start at our delta T crit for hetero is going to be the amount of undercooling we need to start is going to be less. So again, is less or than delta T crit homogeneous. So again, the delta T crit is the difference between Tm minus T, where your curve just starts to nucleate particles. So this is Tm right here. So this is my delta T crit of nucleation for the green curve. This whole thing is my delta T crit for the blue curve. So which curve is homogeneous? Which curve is heterogeneous? Well, the delta T crit here for the green curve is smaller. So this is hetero, and this is for homogeneous. You could also tell that by, again, where's the peak in this curve? So we see here that for the green curve, we hit our maximum of nucleation growth rate at much higher temperatures than the blue curve. So again, it's easier to nucleate. We don't have the driving force, to nucleate particles, or again, we're going to need more nucleation for homogeneous nucleation. We're going to need more undercooling because we need to fight against this surface area term. For the heterogeneous nucleation case, we have less surface area, so we don't need as much undercooling here, the delta T. So you need this much delta T to hit your maximum. We only need this much delta T for heterogeneous. So that's it. So problem 1 done. We'll get into problem 2 in the next video. So let me know if you have any questions, and yeah, I'll see you in the next one. Bye.